So you will find for delta x1, the equation of motion there should be in terms of the time that's given, can be in terms of the acceleration that's given, initial velocity, we concluded that. So the equation that has displacement that relates to this will be, we don't know the final. So for our equation of motions, let's say the first one, equation number one, says you've got your V being equal to, or V final, equals to V initial plus AT. It's nothing to do with displacement, that one. Number one. Number two, displacement. Okay, let me say V final squared equals to V initial squared plus 2A delta x. That is the second one. Equation 3 is in terms of delta x equals to initial times delta t. So this t can be delta t, still the same. So initial times delta t plus half acceleration times delta t squared. Those are our main equations. And so we can find displacement from either equation 2 or equation 3. Equation 2 or equation 3. So the first part of the motion, we have time, we have acceleration, we have initial, we don't know the final velocity there, right? So since we don't know the final velocity, we'd rather just use delta x1 is equal to V initial times delta t1 plus half A delta t1 squared. But the good thing, V initial, where is V initial? It's 0. So this goes out. And what we have, we've got half of what is A, 2 centimeters per second, 2.0. So remember that centimeters will deal with the units at the end. Delta t, our time there is 10 seconds squared. So half of 2 is 1, and then we have 100, and the unit for distance is centimeters. So delta x1 is 100 centimeters. Show with a thumbs up if you can follow. Are we together? Okay. Okay, so you want to say something? Okay, Ashton, thank you for that confirmation. You want to say something? Or it was a confirmation? I saw it was like you raised your hand there. But it's fine if you can follow, then that's good. We continue. That's good. We should continue then. So now we find x2. With x2, what do we have? We have the time again, we have acceleration, but we don't have initial velocity. We don't have final velocity. We only know the position. So remember, what is x1? X1 is a x. Okay, delta x1 will be x1 minus x initial, where x initial is 0. x1, we found x1 to be, or let me say delta x1 to be 100. So that makes x1, the position x1 to be 100. So which means we now have 100 here, 100 centimeters. So we need to find the position x2. We need to find the position x2. So considering the equation, the same equation here, this equation requires us to have the initial velocity, the time, which we have, acceleration we have, but we just don't have that. The other equation, v squared, vf squared, requires v initial squared, acceleration is there, so that we find this as the only unknown. So in either case, we have one unknown, and so that means we need to find the velocity after the first part of the motion. Yes, Matthew, you have a question you can ask? Yes, Matthew, you can unmute and ask if you have a question. I hope I can also hear you from this end. Let me just test this. If I can't hear you, please can you try and type? Okay. I hope it's not the problem with my phones, or otherwise that hand is just hanging there. But no problem. Let's continue. Okay, I definitely won't be able to be hearing anything here. Fine. Okay, so we can find the final velocity for the first part of the motion using equation 1, which is simple because we've got those other parameters. So V1, which means V1 will be equal to V initial plus A1 times delta T1. So V1 becomes, or V initial is 0. So that's 0. And acceleration, we're given an acceleration of 2 centimeters per second. So we've got 2.0 multiplied by delta T. The delta T1 is 10 seconds. So we've got 20 centimeters per second as our velocity. So coming to this motion, the initial velocity is 20 meters per second. It's 20 centimeters per second, sorry, 20 centimeters per second. So applying the second equation of motion, this one, we've got, no, it's actually the third equation. The third equation, we have delta x2 equals to, so this V1 which we're finding is the initial velocity in the second part of the motion. So that's the 20 multiplied by delta t, which is 20 seconds again. Delta t2 is 20 seconds. V1 being 20 seconds, so V initial is V1 there. Then plus 1/2. What is A? It's minus 1 centimeter per second squared. And delta t is the same, 20. So this and that gives us 10. And we've got 400 minus, minus 100. That's 10 squared, half 80 squared. So this gives us, sorry, I was not supposed to even do this. Just this is wrong maths, guys. Sorry, this is 20. So this is half. Let's just leave no shortcuts there. Half of that. So this 20 gives us 400, and half of 400 is actually 200. So we have minus 200 there. We have minus 200. So this gives us 200 centimeters for delta x2. So what did we say about delta x1 and delta x2? Delta x1, delta x2, you sum them together, they give you the final position. They should give us the final position. So that's 100 plus 200 centimeters. So in as much as this body, say I can't unmute myself. Someone can't follow. Matthew can't follow. Okay, the sound. Okay. Let's admit this one. All right. I think I've got an idea of what to do there. Okay, I think that's sorted now. Okay, try to say something with this Mothia. Try to say something. I hope I will be able to hear you this time. Try to unmute yourself again. Let's see. But it's fine. I'll go over this again. I'll repeat what I've just been saying, if that's okay. So what we have said so far is this. What we have said so far is this. Remember the question: a particle starts from rest. That means our initial velocity should be 0 because it's at rest. That's number one. And it moves for 10 seconds. That's we called. So we've split this motion. So we're calling that 10 seconds T1. So it's the time it takes to carry out this motion in the first part of what is described in the question. So that's 10 seconds. And in that 10 seconds, its acceleration is 2 centimeters per square second, right? Then for the next 20 seconds, which means after accelerating for 10 seconds at 2 centimeters per second squared, the next 20 seconds it is decelerating with a negative 1 centimeter per square second. What we need to find is the position, which is the displacement basically, which is the displacement of this particle, which gives us the position. So if you look at the description of the vectors there, it's starting at x equals to 0. It's accelerating in the positive direction as the velocity or as its motion, which is in the positive x direction for 10 seconds. Then while it is moving, because it picks a velocity, it starts decelerating or reducing that velocity in the same direction, which means displacement is increasing, but at 1 centimeter per square second. Now we need to find the position of this particle after 30 seconds. Good. So when we do that, what we have from the information given in just this short description is all this information that you see here. X initial, the initial position is 0. Delta t, which is the time it takes to change its motion, or the change in time when it traverses at 2 centimeters per square second, is 10 seconds. And the acceleration there is the 2 centimeters per square second. Then the initial velocity, because it starts at rest, is 0. That's a deduction that you have to make always. And then the displacement, while it carries out this motion in 10 seconds, should be x1, which is the displacement traveled, minus the initial position x0, okay, or x initial. So that's why we have this. But to find x1, delta x1, which is the displacement, we have to apply the equation of motion. Delta x1 is equal to initial velocity times t from ut equals to half a t squared. So that's your initial velocity times the change in time plus half a times the change in time squared. But because initial velocity is 0, I just had a notification sound there. What's happening? Okay. So because the initial velocity is 0, we eliminate. Let me change my color there. We can eliminate this because vi is 0, right? And then we remain with half a delta t1 squared, where a is 2, t delta t is 10. So 10 squared, 100, half of 2 is 1. We remain with 100 centimeters. I hope you caught that. That part of the motion, it covers 100 centimeters. Now, it begins to decelerate. When it decelerates, it starts at a certain position, which is 100 centimeters from the initial. So it starts at x1, which is 100 centimeters in terms of position, and it decelerates for 20 seconds with a deceleration of -1 centimeter per square second. We don't know what the final velocity is, it's not given, but we know that this displacement, when it's decelerating, is delta x2, and it will be equivalent to the final position xf minus the x1, which is minus 100 centimeters. So what is that final position? So for us to find it, we do the same thing. Delta x2 is equal to the initial velocity, which we have found. Well, how did we find initial velocity? Because we didn't know this part of the motion. How do we find it? We have to use equation 1. Initial final velocity equals to initial velocity plus at plus a1 times delta t squared. So this final velocity is therefore, since initial velocity is 0, it's just a product of the acceleration times the time, which is 2 centimeters per square second. For 10 seconds, it gives us 20 centimeters per second. So now we found the velocity when it finishes the first 100 centimeters. And that's the velocity that we use here, because it's the initial velocity to the deceleration. Okay, so with that velocity, we multiply it by time, 20 seconds, plus half of the acceleration, which is -1, times delta t squared. So this is delta x equals to v I delta t plus half a delta t squared. Okay, so that's what we've done. The a is a deceleration, is -1. The initial velocity is the velocity when it starts to decelerate. So that's how we use those values there. So what is 20 by 20 is 400, and what is 20 squared is 400 again. Half of 400 is 200. So 400 minus 200 gives us 200 centimeters. The overall displacement, or the final, so x final equals to x initial plus a overall displacement, delta x, right? So this overall displacement delta x is apparently x initial, which is 0, doesn't matter, plus x1, delta x1 plus delta x2. So you add this, gives us the overall displacement. So since x initial is 0, delta x1 What is that? 100 centimeters. Delta x2, 200 centimeters. We get an overall position x final of 300 centimeters. 300 centimeters. Okay, I hope that's clear enough. Let me just check over if there are any questions there. Yeah, the stream is buffering a lot today. No noise from there. Yes, so the live is actually lagging. There's a lot of buffering from this side. I think the connectivity is quite poor today, so you have to bear with us, guys. There will be a lot of latency between what I'm sharing and what you'll be seeing on that side. So that delay, you can bear with me. It should be around 10 seconds or so. But yeah, we can work with that. So let's go to the next set of questions. Our next question here is question number 12. This is a vertical projectile. So with this, a stone is thrown from the top of a building with an initial velocity of 20 meters per second downward. The top of the building is 60 meters above the ground. How much time elapses between the instant of release and the instant of impact with the ground? So we have a projectile motion in this case. What is the given information? What is the given information from this question? We have to collect that data. What do we know? What do we know? So the first thing, initial velocity, VI, is 20 meters per second. And remember, this is a vector, so the directions become important. In this case, it says downward. So we have taken the downward motion to be positive. So it's not always that you would take upward to be positive and downward negative. You have to just assign your directions. And once you do that, you should be consistent, or you stick to your assignments. So if you take the downward direction to be positive, then it means anything going in the opposite direction, which is upward, should be negative. In this case, everything, we are considering the motion, in this case, downward, to be positive. Then the top of the building is 60 meters above the ground. So in this case, when we traverse this displacement downwards, so it's going to be 60 meters in the positive from the initial point. So our reference still should be the upward position. Then how much time elapses between the instants? So we need to find time. So we've got delta. We can say delta x or delta y, because it's now in the vertical, is equal to 60 meters. And what else do we know? We've got an acceleration, which is 9.8 meters per second. It's positive also because it's downward. What else do we know? We need to find delta t, which is the unknown. So this is all the information that we have, and we need to find the time it takes to get to the ground. The time to get to the ground. So which equation do we use now? That's the most important question. Which equation do we use? Displacement is given. What else is given? Initial velocity given. Acceleration given. You just need to find time. So delta y delta y will be equal to initial velocity times delta t plus half a delta t squared. So delta t becomes our unknown. The displacement in this case. So depending on your assignments anyway, the signs will vary. So since we've said downward is positive, we use 60. And the initial is 20. Delta t, we don't know. And plus half. The acceleration we said is positive. And delta t squared. Usually what you would do, if you would have considered upward motion to be positive, then that means your delta y becomes negative because it is moving from the highest point downward to the ground. So you would use minus 60 there. Your velocity becomes negative as well, minus 20 there. Your, what do you call this? Your acceleration is also negative. It will be minus 9.8. So you'll see that you introduce negatives on all the terms. So the equation still remains the same. 0 is equal to, that's 4.9 delta t squared plus 20 delta t minus 60. So this is now a quadratic equation in t. This is now a quadratic equation in t, where to find delta t, which is just like our x, so this is like 4.9x squared plus 20x minus 60. So your coefficients are such that this is a, okay, I didn't select anything there that I want. So this is a x squared plus bx plus c, where your a is 4.9, your x, the unknown, is delta t, your b is 20, your x is still delta t, your c is minus 60. So to find x, the quadratic formula requires that x will be equal to negative b plus or minus the square root of b squared minus 4ac, everything over 2a. That's your quadratic formula. So this is a beautiful equation. It works magic. Delta t is our x, should be equal to negative b, which is negative 20, plus or minus the square root of negative 20 squared. So not negative, it's actually 20 squared, minus 4 times a being 4.9, times c minus 60, close bracket, and like that. Everything all over 2 times a. We do the calculation. We can do the calculation. Let me see if my calculator behaves here. Where is the calculator?
It's open for now.
Hey, finally I can hear someone speak.
T is open for 9.
Okay. T is equal to what?
0.49.
0.49.
Yeah, 2 decimal place.
How did you calculate that? Can you cross-check your calculation again? Otherwise, I should have done something wrong there. Can you just cross-check the calculation again?
Actually, T is 2.01.
2.02, right?
Yeah.
Yes, 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 perfect. Thank you for correcting that, but that's fine. That's fine. It's part of the mistakes that you do. So, besides everything else, the first thing you should be able to identify your motion, see the equations, the directions are important, which equation you're gonna use is important, and then make sure you don't do errors in your entering of the values to get the final answer. So that is basically what is of most importance there. So it's 2.02. 2.02 should be your answer for this question. That should be 2.02. Okay, I think we can move to the next question. Any question regarding this? I'm sure this is quite straightforward. There are two ways in which you can work it out anyway, besides this. Considering you have all the given parameters that we put together. Where did we put together the parameters here? Right? So with this, you could otherwise find your final velocity. Then you use the final velocity to get. So remember, you've got final velocity v equals to u plus at, or delta t is what you want to find, eh? U plus at. Initial. Okay, so v squared equals to u squared plus 2as. So from that, you can find your final velocity, v final squared equals to v initial squared plus 2as. And the v initial is 20 squared 2 times 9.8 times 60 in the same direction. So the directions are still the same, acceleration in the same direction as the change in displacement. So we've assigned the positive to be the downward. So this would give us 400 plus 120 times 9.8. I don't know what that gives us, but let me see. If I say 20 squared plus 120 by 9.8, 1576. So we're looking at VF squared being 1576, and the root on both sides gives us VF equals to 39.9, I hope, to the power half. 39.7. So this is 39.7 meters per second. So we find the final velocity from this, because we have this given, we have that given, and that given. With final velocity, we come here. V final equals to V initial plus A times delta T. So because this we now have, that we now have, that we now have, we find delta T. 39.7 equals to 20 plus 9.8 times delta T. It's your only unknown. So 39.7 minus 20 gives us 19.7, and divide by 9.8, we get delta T, which is 2.02, the same. So you just have to choose whichever. This is the long method, because you are going to apply two equations, which are all summarized by this golden equation. So this golden equation, you'll never go wrong. You should just teach yourself to like using the quadratic formula. It's just simple. The calculator does the rest, so don't worry about having square roots and all that. You just put your figure values there, you get the final solution seamlessly. Okay, I think we have to move on to the next part. Let's see where we are. Where are we? Where are we? Okay. Question 13. Okay, so the answers anyway, the answers there, the answer is A. The first one sorry, I didn't check that. That's 300 centimeters. 300 centimeters should be 3 meters. So that's the first part, and the second part done so far. The position of a particle moving along the x. This is another interesting one. Position of a particle moving along the x-axis is given by x is equal to 6.0 t squared minus 1.0 t cubed. So this is a parametric equation in terms of t, how x changes with time. So in other words, we could write this as x being a function of time. You have done functions, right? X as a function of time is 6.0 t squared minus 1.0 t cubed. Okay, where x is in meters, t in seconds. Now, what is the position of the particle? Yes.
But I can't.
You're breaking. You're saying?
I'm still up on the previous screen. I can't see the new one. Like the problem we are doing like right now. I can't see it.
Okay. Thank you for that. Let me see what's what here. Can you see it now?
No, sir. No.
What is happening? What are you seeing? What are you seeing on the screen? Is it the one where I'm writing or the question?
It's the one whereby the statement is saying that a stone is thrown from the top of the building with an initial velocity of 20, like the previous one said.
That's what you see in terms of the question.
Yes, sir.
Wow. Let's see. And you are seeing it from here on Teams or on the YouTube platform?
Or on Teams.
On Teams.
Yes, sir.
Okay. Thank you for raising that. Let me see what's happening. Still same problem? Nothing has changed.
Yes, but you can still continue. I will watch it on YouTube.
Okay, that's fine. The YouTube one is showing the current screen.
No, not yet.
Not yet.
I haven't want.
Okay, no,
I
it's
haven't
fine.
want.
That's fine. Let me just try and reshare. I'm just gonna stop and restart the sharing again. What did it just do? Kick me out. All right. Okay, just bear with me, guys. Something happened to the Teams platform. If you're on YouTube, I'm just gonna have to wait a bit until I restore the pages that just crashed. Oh, sorry about that, guys. The system just kicked me out. It crashed. Just have to start sharing everything all over again. I'm sure it had frozen. The moment I just stopped sharing, just threw me away. But anyway, that's fine. I'll just reshare and see if we're gonna win this time. That's the beauty of technology. OBS. Okay, I hope you can see the screen. I hope the current screen is visible to you guys. Okay. On Teams, Omio, can you see the screen, Ashton? Can you just confirm, please? On Alena, just let me know if you can see this screen. Kwazi, are also here with us. Just let us know, please, so that I know if everything is in order. But nonetheless, I'm just gonna continue with the last part. So here we were to find the maximum, the position of the particle when it achieves its maximum speed. So what are the requirements there? What are the requirements for us to be able to find this position? What does maximum speed mean in the positive x direction? So for us to get to that, we need to find the velocity of this particle, and this is given by the differential with respect to time of the position. And so a differentiation of x with respect to t gives us 12.0 t minus 3.0 t squared. So the velocity at any time t is therefore given by, so this is velocity. 12t minus 3t squared.
Sorry, sir, but you are on mute.
How is that possible? Because my mic is... Oh, this thing is gonna be a lot. You still can't hear me? You still can't hear me? One, two, 1, 2. Can you hear me now? Hello, can you hear me? Is it any better? You guys still can't hear me? Hello? If I check my mic this side, it seems the audio should be clear. I don't know why you guys can't hear. I don't know why you guys can't hear.
I can hear you, sir.
Oh, good. So it should be something else. There should be some problem somewhere else. Anyway, so what were we saying? If we have velocity like this, it means the velocity with respect to time is given by 12t minus 3t squared, meaning if t is 1, you've got 12 minus 3, which is 9 meters per second. If t is 2, you have 12 times 2 minus 3 times 2 squared. So that will be 24 minus 12, like that. So you can find the velocity, but there's a point where the velocity reaches maximum. And according to that question, that's the point where the particle ceases to have acceleration, so achieves its maximum speed. At maximum speed, it means it's no longer accelerating. So we want that point where its acceleration is 0. So we go on further to find d squared x over dt squared, which is the acceleration, and we differentiate the velocity. We find 12 minus 6t as our acceleration. But then, what does that mean? It means at the point of maximum speed, this acceleration is equal to 0. So it means 12 minus 6t gives us 0. And therefore, that means that's when t is equal to 12 over 6. And that's 2 seconds. So at 2 seconds, the object will experience its maximum speed. But then the question doesn't want us to find time. It wants us to find the position when this happens. And that position is by substituting 2 into the parametric equation. X as a function of time when t equals to 2. So we go on to express our x as a function of 2 will be equal to 6.0 times 2 squared minus 1.0 times t cubed. So this is 24. 6 by 2 squared is 6 by 4. 24 minus 8. This is 16 meters. So this happens 16 meters from the starting position. That should be 16 meters. And we can confirm that if that's possible, the question should enable us to confirm that. So there is our 16 meters there, which is fine. Okay, so that's 16 meters. Then the next question, if we are fine with that part, our next question. A car travels counterclockwise, so that's anti-clockwise, around a flat circle of radius 2.5 kilometers. So that's 2.5 kilometers. And the car is traveling around that circle counterclockwise. So we have V. If this position is 1, V1, position 2, V2, position 3, V3, position 4, V4. So it's going in a circle of radius 2.5 kilometers counterclockwise. The constant speed is 20 meters per second. So V here is 20 meters per second, always, it's the speed. But this one is 20 meters per second, what? East for a velocity. 20 meters per second, north. Then this one is to the west. That one is 20 meters per second, south. That's how the velocities are different. So the magnitude of the motion is the same, but what differs is the direction. So because direction is different, velocity is different. Because it changes direction, it also changes velocity. In as much as it's keeping the same magnitude of the velocity or the same speed, this body has an acceleration. So it is 20 meters per second throughout, but it has an acceleration by virtue of changing direction. Okay. So with that, it means this body has an acceleration, and that acceleration is always towards the direction of the change. So it actually causes a velocity to change from east to a resultant, which is north. So the change in direction will be in that direction, in that way. So this is the delta V, this is V3, this is V4. So the change, if you look at it, is in that direction. And what is that direction now? You find this direction is actually on average acting from that point such that it is towards the center. So it is actually acting towards the center to give that change for V4. So V4 is that, V3 is that this change in velocity is towards the center, and so the change in velocity over time becomes the acceleration. So the acceleration of a body that is moving around a circle is towards the center. So it's centripetal acceleration. Anyway, what does the question want us to find? We need to find this acceleration. We need to find this acceleration. So how do we find acceleration for this body? Acceleration, centripetal is v squared over r. So this is 20 meters per second squared over a 2.5 kilometers, which is 2,500 meters. So what does that give us? What would that give us? 400 over 2,500. 400 over 2,500. 0.16. So I'm getting a 0.16 meters per second squared as the centripetal acceleration. So always at any point, whether we are at point 1, point 2, point 3, or point 4, the acceleration is 1.6 meters per second, its magnitude, but the direction changes. The direction of the acceleration changes. So if a car is at point A, as shown in the figure, what is the acceleration? So now we don't know point A because we don't have the diagram, unfortunately. We don't know what point A is. So if I would say, let's say if the point is point 1, if the point is point 1, the acceleration we're saying is towards the center, so it will be south. If the point is point 2, it will be east. If the point is point 3, the acceleration is in the direction north. So this is east, this is south, this is 1.6 meters per second north. Or if the point is this one, then it's 1.6 meters per second west. So that's basically what that acceleration should be. The magnitude of 1.6 meters per second, and the direction is given by the direction towards the center in general. The direction is the direction towards the center. So we've got a 0, which is out. 1.6 meters per second squared south will be when it is at the top of the circle. 1.6 meters per second squared east will be when it's at point number 2, which is to the left, the tangent to the leftmost part of the circle. And 1.6 meters per second squared north will be when it's at position 3 at the bottom, or 1.6 meters per second squared west, which is the position to the right, position 4. So the actual position is this position, position 4. Our car should be moving like that, in that direction, with an acceleration to the west. So that should be how the diagram should have looked there. Should be to the west. So we are at the end. Unfortunately, this became long because of the buffering, but it's fine. We managed to do what needs to be done. Apologies for those that asked questions and were not responded to due to these glitches. I can't promise we'll do it better next time, but I'm sure the traffic, the data traffic and the connectivity will definitely be better the next time we meet. So with that, we look at our next question. And for this question, the question reads, I just have it shown there. The initial speed of a cannonball. Okay, so this is now for arsenal fence. Okay, we've got a cannon. Okay. And it releases a ball which projects like that. What's happening there? Admit, okay. So we've got a cannonball released, and it will definitely make a projectile motion like that. And the speed with which it is released is 20 kilometers per second. So we've got a speed there. Let's see if so when it's released there, that speed is 20 meters per second, 20 kilometers per second. And it has to hit or strike a target that is 3 kilometers away. So from roughly that point to the target, this is 3,000 meters. Okay, the target is 3,000 meters away. So we would assume that let me even say the target is even level with that, so that we don't overcomplicate this. But even if that's the case, that should be fine. That should be fine. Just assume the height of that cannon is. Otherwise, let me just do this. I could do this. No. I want to select. Okay. I'll place this on here. Okay. Then what we have then, the blue will be that line, and the velocity of 20 is the launch velocity, so we take that down there. So we launch here at 20 kilometers per second. Okay, so that's our diagram. Cannon launched like that. The target is 3,000 meters away. So what we need to find is the minimum time of flight for the ball. The minimum time of flight for the ball. So this cannonball just goes there, and when it's launched at 20 kilometers per second, what will be the minimum time of flight? So apparently this is a very simple question, because for the cannonball to reach the target very fast, it means at least this cannon should launch at an angle such that theta is basically 0, right? So which means it's a horizontal launch. Instead of launching it high like this, then this should be horizontal launch, so that this is the speed in the horizontal direction, right? Horizontal. So remember our V cos theta, right? It should be maximum, is maximum when theta equals to, when cos theta is 1, that means when theta is equals to 0. Okay, so that means V should be 20 kilometers per second and theta should be 0. So V cos theta should be the component that's equal to 20 kilometers per second. And so as such, theta will be 0, V will be 20 kilometers per second. So with that, we know that the horizontal direction x component is V cos theta t. And this is 20 kilometers, which is 20,000 meters per second, multiplied by t, to cover a distance of 3,000 meters. So is it 20 kilometers? 0.20 kilometers, okay. It's actually 0.20. So it's not 20 kilometers, actually 0.20. That makes it 200 meters. 200 meters. Okay, 0.2 kilometers is 200 meters. So when we divide by 200 on both sides, what do we get? 15. So this is 15 seconds is equal to the least time. But remember, this is a cannonball, and it's in an environment where you find there is also drag or air resistance. So ideally, this will be the least without or assuming air resistance is negligible. But otherwise, the value should be somewhat closer to 15. It should be greater than 15. The minimum time, T min, should be slightly greater than 15 seconds. And hence, according to the solutions that we have here, we can do the elimination. Let's see what we have. We have 16, 21, 24, 14, and 19. 14 is out because it's less than 15, which we should get with horizontal launch and no air resistance. Then the list that we have that's closer to 15 is 16, and 16 becomes our best answer. So that's the reasoning behind this question. The minimum time should be 15 seconds without air resistance. So considering air resistance, then the time can actually be at least 16. So that's basically the reasoning around this. So thank you guys for your time. I hope you were able to learn something from this. Apologies for that glitch in the connectivity and everything, but that's what is expected when the network is not so good. But otherwise, from me and everyone at Yebo Physics, we want to wish you a great weekend. If you have questions, this is the time. We'll be able to assist you if you have any. But if you don't have, then enjoy your weekend. So I'll open room for questions now. If there is no response, then I'll just stop the recording and we can call it a day. It can be questions regarding this or questions from the previous tutorials or otherwise which you came across as you were revising that we will be able to help you with.
Oh, okay, sir.
Yes, good.
Can I please ask?
Mm-hmm.
It 4,000 that you divided by 200.
Yes, 4,000. The 3,000.
It's 3,000.
Yes, it's 3,000 from 3 kilometers.
Okay. So that's our range.
That's the range, yes. That's from the range.
So say if you are given two, like, what can I say, 2 points of a position, say, how do you identify about like this one is a range and the other one is like how do you identify the range, say?
Okay, I think yeah, so the issue of range, you have to be careful because when you're given range, remember, if you saw my diagram, I had to take this cannon to this level so that the point of launch to the point of target are on the same height, same horizontal distance. So you would find if the ground is down here, let me see if I can use a different color for you. Purple is there. So let's say this is the ground, right? That would mean the launch would progress to that point to strike the ground. And that point, let's say it's around 3,500. So 3,500 meters, 3.5 kilometers. So when we are using our equations, because you've got equations for the equation for range, I think it's u squared sine squared theta over 2g. U squared sine squared theta over 2g. I think that's the equation you usually use for range. It applies when you are here, right? But when you calculate below, what do you call it? below the launch height, so there is a delta y there. So if it lands below the launch height, you can't use that same equation where you have got did I get that question for no? It's the one with sine 2 theta, I think. So range, I think it's should be u squared sine 2 theta over, I've forgotten whether it's 2g over g, but whatever is that equation is sine 2 theta. It applies when you are considering the same horizontal distance. But then, if the distance is 3,500, this equation won't apply. It only applies to give you the x. Usually, I don't want to confuse that term range and this x distance or the horizontal distance. Horizontal distance or horizontal displacement generally is given by u cos theta multiplied by t. So it can be at any position. It can be u cos theta when t is at some whatever value. Let's say after 10 seconds is there, or after 2 seconds is there, after 4 seconds is there, after 8 seconds there, 10 seconds, it finishes the range is there. But after 12 seconds, this still applies to get you to what? To get you the value of x, of generally x. But this equation won't give you what happens there after, let's say, if that is 10 seconds and this is 12 seconds. This equation cannot find the value of x at 12 seconds because it has nothing to do with the angle of launch and the rest of the values and your u and everything. So this is only applying when you pass this same horizontal position. So I don't know if you have seen or how do your textbooks really present this term range and the term horizontal distance, but you can't use the range formula. If this is your range formula, then this range formula only applies when your object is coming to the same level as when it was launched for a projectile. Then the rest, let's just call it the horizontal displacement or horizontal distance. From launch, whether we are landing somewhere higher than when we the launch height or at the launch height, this will also apply for here where you calculate your range, or below launch height. This is the universal equation for the horizontal distance. I don't know if that answers your question.
Yeah.
Yes.
Thank you.
Okay, very good. Thank you for that question. So yeah, it's something that I've seen. You need to be careful with regards to when you are calculating your range and your range is usually when you land at the same horizontal position as the launch position or launch height. But the rest, any other position, we don't call this range. So when you are here, this is not range. This can't be range. This is just a horizontal displacement. The range, that term particularly, or in most cases, it is used for finding the maximum distance at the same height as the launch that the projectile will reach. That's my understanding of range. But any other position, if it's not described otherwise, it's just generally, in general, your equation should be the one for horizontal displacement. Okay, thank you for that question. Any other question? Okay, someone said I'm understanding the content, but the formula is something else. Okay. I think that was the formula for, sorry guys, I had not checked what was happening on YouTube. So, driver 517 is the name, right? I hope you are still here with us. But anyway, the formula that you were referring to here, you gave us 0.20 kilometers per second. You were correcting me when I was saying 20 kilometers per second. That's fine. Thank you for that. So you were actually concerned about this question. So for this question, I'm not going to derive the formula for you. It will be something else. And you won't like it anyway. The derivation, it's an interesting one, but it will take us time. But the question for centripetal acceleration can be given as omega squared r, which is the square of the angular velocity or angular frequency multiplied by the radius. Or since omega is equals to V over R, then which means omega squared is V squared. Omega squared is V squared over R. So this is V squared over R squared multiplied by R. That's how this comes to V squared over R. So this is just the formula. This is the formula for your acceleration, the centripetal acceleration. Usually you get it in your formula sheet as well. So you'll come across that formula a lot of times. You have to know this formula. Remember, even when you're calculating the centripetal force, you say mv squared over r. So you're just saying mass times acceleration there will be mv squared over r. So you're just saying this is your acceleration. Okay, or m omega squared r. So I hope that's where your question was when you said I'm not understanding the formula, but the content is fine. So yeah, that's where the formula comes from. It's one which you can find in your textbooks and the like. So I hope that helps you drive a 517. Okay. Okay, I have a question. Who is this? Who has got questions? IQ. Let's hear the questions. What are your questions?
Regarding the projectile motion, I want to understand this. So, if we are projecting a body, so we are treating the horizontal motion and the vertical motion respectively. So our horizontal motion is constant, while our vertical motion changes throughout the trajectory. Yes, that's what I'm trying to understand, Babo. So like our UX will always be constant from, suppose if we have point A, B being the highest and C. So from point A to C, our horizontal motion will stay constant, like UX will stay constant, while this UI changes through the what you call
the motion, yeah. Okay, so you want to understand why that why it's like that, why the other one changes and the other one doesn't change.
Yes, sir.
Okay, good question. So remember, when we launch, we've got an object. It's launched with an initial velocity v at an angle theta. Then, because of that angle, we've got components in the x and in the y. And these components require that the vertical component is v sine theta. We talked about this last time. It is the one that is opposite the angle, right, in the region that is not subtended by the vector itself and the component. And the horizontal component is v cos theta, the one that subtends the angle. It is the vector and the component, the angle between them being theta, so it becomes a cos theta component. Okay, so what happens is when we are moving in this direction, with if we neglect a resistance, it means there is nothing that stops this object or this component of the velocity, or that hinders it or decreases it. But the one that goes up, when it goes up at that point, okay, I think I can draw in some nice depictions here. So remember, we've said our v sine theta starts there, whereas v cos theta is this one, right? When we are at this point, v cos theta will be that, whereas this one is still the same. So v cos theta still maintains the same, but this one, you can see my arrow is now small, v sine theta. When we are here, v, it's only v cos theta. V sine theta, there's nothing. When we go down at this point, v cos theta still remains same, v cos theta. V sine theta starts increasing again. Then when you are here, v cos theta is still the same. And here, v sine theta regains the same value but in the opposite direction. Okay, so this is now minus. Anyway, these are now minus v sine theta. Okay. So let me call it, do I want to call it v1, v cos theta, v1, okay, whatever the case. But the whole essence is at that point, because the velocity, so maybe I have to define, let's say this is v1. Yeah, something like that. So the angles also changes. So this becomes v1 cos theta 1, this is v1 sin theta 1. Here it's not going up or down, so Vy is 0. There's no Vy. But, or let me call it V2. But Vy, yeah, Vy is fine. Then this is V2 cos theta 2, V2, V3 cos theta 3, and V3 sin theta 3, then V4, theta 4, V4, and theta 4. Okay, so why I'm doing that? Which black? Okay, so initially we launched with a velocity v which could be 30 meters per second, but in the vertical, because you've got gravity, right? You have gravity. The vertical component decreases. When you get to the maximum, your Vy is 0, because gravity acts opposite to this vertical velocity, decreasing it each time, right? Decreasing it each time until it gets to 0 there. Whereas there's nothing acting against the v cos theta, so v cos theta remains throughout the motion. When we pass the maximum height at b, we start accelerating downwards. So the vertical component begins to increase. Then we have, in this case, a value v3 sin theta 3, which is equal to the negative of v1 cos theta 1. So this is minus v1 cos theta 1 if they are at the same height. So assuming they are at the same height, v1 cos theta 1 is equal to v3 sine, sorry, why am I saying cos? v1 sine, so because the vertical component is always sine, in this case it's always sine, so it will depend on what your theta is. So sine theta 1, v1 sine theta 1 minus v1 sine theta 1 is equal to v3 sine theta 3, because they are at the same height, they have the same x component but opposite y components, so that's why there's a negative there. When you get to point C, v cos theta is still the same, so v4 cos theta 4 is equal to v cos theta, this initial one. They're the same, it has not changed, so I've used the same R. Same, 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 and same. There is no deceleration if there's no air resistance. Then you would find the y component is downward, so this v4 sin theta 4 is actually equal to minus v sin theta, the initial one. So it's the negative of this, same magnitude as the initial. But when we go down, if it were to go down and continue like that, you'll find that this downward velocity increases beyond the magnitude of v sin theta, whereas the x component is still the same. So that's the reason why the motion in the x has no acceleration, it is constant. Whereas the motion in the y is acted upon by gravity. So it decreases when we are going up until it gets to 0 at maximum height, and then increases downwards until probably you hit the ground.
Okay, so hey, yeah, thank you so much. So, yeah, I just wanted to be enlightened, Wabo. So, all right, so conclusionally, you are saying that, okay, from point B to C, it is equals to point A to C, but in the opposite direction.
B to C is equal to A to B in the opposite direction, yes. Symmetric.
Yes, so, all right, and then what else? Okay, I think I'm good right now.
You think you're good right now? Okay, well done. That's great. So that should it's good for that helped you. Right, thank you for your question. Anyone else? Any other question?
Yes, say one more thing. Can I discuss something again, Manish?
Yes, yeah. Go on. Feel free.
All right, so when we give the body an initial velocity, as it rises while approaching B, it decreases until it becomes 0, and then from B to C, the rate at which it goes down, it's much more faster because of the gravitational acceleration acting as a negative quantity when it goes down.
By faster, you mean faster than when it went up?
Yes, than it went up. Yes, sir.
So that's quite tricky to say faster, because it takes the same time to get to B from A as it takes to come from B to C. It takes the same time because it is under the same gravity. So let me just do a simpler one. It is being acted upon by the same gravity. So let's say we throw a stone up, right? We throw it up. It reaches maximum height, then it comes down, right? So you would find there are a lot of let me say common terms. Height being the first one, delta H, it moves the same distance from A to B, right? It has the same gravity acting on it from A to B. It has the same, it should take the same time to go from A to B, meaning delta T up should be equal to delta T down, right? Then if it's starting at A with a high velocity, it reaches B with 0 velocity. So V initial is high at A, then 0, V final 0 at B, whereas V at B being 0, which is low at B, and V at C, let me call it C when it comes back to the past the same point, being a high, right? But it's high with a value that is equal the value of V initial. So which means it loses a velocity when it gets to B, it gains the same velocity by the time it gets to C. And it does that over the same distance under the same acceleration. So the time it does to lose the velocity, because it loses as a function of the same gravity, it will gain the same velocity over the same distance because it's the same acceleration that it is, same rate at which it, remember acceleration is rate at which you change velocity. So it changes the velocity going up at the same rate, it changes the velocity going down at the same rate. So the rate of change of velocity going up is basically a loss in velocity, a decrease until we get to 0. So because it will have the same rate at which it gains, it will gain the same velocity at the end over the same distance. And so it takes the same time. So now why am I saying this? It's because it doesn't go faster. It is increasing. It is just increasing when going down. But it is increasing at the same rate, which is gravity G, at 9.8 meters per second every second. So when going up, it loses 9.8 meters per second velocity every second. When coming down, it is gaining 9.8 meters per second velocity every second. That's what the acceleration is. So because the acceleration is the same, it will gain the same velocity. So it's just not faster. It is a increasing velocity when going down, but at the same rate as it decreased its velocity when it was coming up. So the rate is the same there.
All right, understandable, Minera, it's understandable.
Nice
So
one.
as I go up from A to B,
Mhm.
I'm decreasing, but from B to C, I'm increasing with the rate that I decreased with.
Very
All right.
good. Very good. Just like that. So yeah, that should be the thing with the projectile motion, especially for vertical projectile. So here with this 2D motion, we are just combining vertical projectile and let me say motion under uniform velocity, because that's the horizontal component. So when we combine them, we get this parabola with this a nice shape for the projectile there.
So in summarization, meaning we are saying that the gravitational acceleration acts downwards. Thus, if I project a body upwards, there is a force of gravity that is opposed by the gravitational acceleration.
That opposes the motion of that body, yes. So the force of gravity opposes the motion of the body that's going up. And that force of gravity is the one that is due to the gravitational acceleration.
Also, the force of gravity is acting downwards also due to the acceleration of the gravity.
Yes. So remember your second law, Newton's second law, F net equals to the mass times the gravity, which is the weight of your body. So the weight is always the weight is always the gravitational force acting on the mass. So if you have a system that is only under gravity, that gravity is the F net if there's no other force. But if there will be other forces, then we will have to find F net as the difference between the gravitational force and whatever force comes into play. But if it's free, what we call free fall is when the gravitational force is the only force acting on a body, and so it is the F net.
All right, all right.
Okay, wonderful. All right. If there are no further questions, guys, we can call it a day. It has been a lovely afternoon having you. Thank you for your questions. You can bring more in the coming week. We'll still be on the platform. We'll tell you if the days change depending on the availability of our tutors. But generally, Wednesday, Thursdays, and Fridays, that's when we'll be here to help you with questions that you have and go on with the topics that you have covered. So from me and everyone at Yebo Physics, let me say goodbye for now.
Wait.
Okay.
Man, it's something that I'm wondering about.
Let's hear it.
Okay, Miner, let's exemplify using a horizontal motion with relation to F net equals ma.
Yeah.
I can say if I maybe let's say I have a stationary object and then I want that object to be in motion. I'm applying what? A force. Then if I'm applying a force, the object will do what? Move in at a particular velocity. Again, let's say we're ignoring the what you call the oppositional forces again. So we're ignoring the oppositional forces, then we push the object. So meaning even so Gushuguti in projectiles, it is also the same thing. When we are giving the body a velocity, there is a force due to gravity. That's the main point, like there is a force due to gravity.
Okay.
I want to understand because the explanation for a projectile, it's saying that it is when a body is given an initial velocity. Yeah, sorry.
All right. Okay. Yeah, I get where you are coming from. So the thing is this: there are two things happening here. When we start with a velocity, like you said, if a body is initially at rest, for it to begin to set motion, it needs a force that drives it, right? That force which drives it should be such that it gives it an acceleration, and the body gains velocity. Because its acceleration, it should increase velocity. But this is not a let me see, how do I put this? This is not a continuous force that is being given to a body. Like when you are throwing, you apply the force and release the stone so that it goes, right? So when you are not always constantly pushing the force, the stone throughout its motion. So there is a launch or a launch force, let me call it that way. Just like in the cannon example, it's the explosion that just boom pushes the cannonball out, right? We don't mind what that force is. What all we know, we're not dealing with kinematics, right? Which is in this case, we don't worry about the forces acting on the system, right? We just are studying the motion itself. The force that caused the ball to move initially is basically a result of the explosion, that is the chemical explosion that happens inside the cannon due to it could be gunpowder or whatever it is. So all that, the nitty gritties of how that force comes by, we don't care. How much that force is, we don't care. We just know that it's a sudden force on the cannonball. The cannonball leaves the cannon at 20 meters. Was it what was that force by? What was that velocity again? Whatever it was, 20 meters per second or otherwise something. In this case, I think it was saying 0.2 kilometers, right? So that was 200 meters per second, right? So it is suddenly accelerated such that when it leaves the cannon, it has its initial velocity. So we start thinking about when it has already been pushed. So we call that initial velocity of 200 meters per second for this example in question. Then when it starts moving now, because it has a component of the 200 sine whatever angle, that component in the vertical starts being acted upon by gravity until it reaches maximum height. That's when the gravity has subtracted all that component of the 200 meters per second sine theta, and it's now zero at maximum height. It cannot go higher any further because it has no more drive in the positive vertical direction. But still it's moving to horizontally because nothing is acting against the horizontal motion. So it continues, then starts moving down. The horizontal motion is still the same because there's no acceleration. Gravity only acts in the vertical. So it starts increasing now. It's a vertical component until it gets to the point where it hits the target. So the gravity becomes the only force that is acting in the motion from the point when we have launched. So the force that launches, we don't care. It just sets the system into motion. It's a great force. It accelerates it, suddenly gives it the acceleration in a very, very small time and gives it the 200 meters per second velocity. So how that happens, the motion, this part of the topic of our topic or of the kinematics or this motion in 2D doesn't really matter what the gravitational value of the gravitational force is and what the value of the force that launches the driving force is. All we know, we have gravitational acceleration acting upon the vertical motion, which is vertical component. So you're right to think of the force that drives it because it has to be set in motion. Yes, there was a force, but it's not part of the calculation that we deal with because we only know it's good. We only know that force gave us a velocity or drove that ball to a velocity of 200 meters per second in an instant. But then it stopped because the ball left the vicinity of where the force was applied and started moving under free fall, which is under gravity.
I know, sir, you said a mouthful, it's understandable. Hey.
Okay, no, it's fine, it's fine. At least I know why if you think the way why you're asking was you want to really see, it helps you understand where you really need to go with your working so that you don't consider things that are not really part of the question. So that's fine to clarify such issues and take them out of the picture. Then you know why it is said to be free fall. It's because gravity is the only force acting upon the motion of the particle.
All right, thank you, Minel. So in summarization, we are only regarding the initial velocity that we have given to the object, and regarding that, we have a gravitational acceleration that is acting downwards.
Yes, good. That's a good summary. All right, we can call it a day now, right? So yeah, I think that's about it for today, guys. Thank you for your participation. I'll see you again in the coming week. And yeah, all the best with your reading and preparation for the coming tests. I'll stop the recording now, and yeah, you can leave the meeting now. Thank you, Kwasi. Yeah, sorry about the audio. I know you. I saw you saying you can't hear. I don't know what was happening, but yeah, that happens. That happens to the rest of us. Okay. Thank you, IQ.